Shakespeare. I wrote this kind of paper presentation thing about a year ago. It was born mostly out of kind of intrigue as to people always say about certain analog filter types. They rave about the mode ladder and diode ladders. But why do they actually sound like the mode ladder and the diode ladder? So I'm going to go over a few kind of common topologies. I'm not touching any OTA stuff, if people know about that. There are books and books and books on OTA filters, and they're, in my opinion, just not really as interesting. So to start off with, I was just having a chat in front about this, analog filters are still really relevant, even in the digital age. I mean, I think everyone here is kind of the same agreement. But yeah, digital filters, they're difficult really to make when compared to analog filters. Why do we want to actually control color in the first place? Well, we want to be able to control the tonal content of a waveform that's sent into a filter. That's the main reason. And how do we do this? How do we apply voltage control to what is effectively a resistor and a capacitor circuit? How do we do that? There are various advantages and disadvantages of each topology. I'll talk about each in hopefully some degree of depth. How do they most importantly sound? I'm going to try and describe the sound of each to you. Hopefully you guys kind of know what each one sounds like. If not, go and listen to these things, they sound amazing anyway. And also where they're used. It's interesting how the actual kind of electronics behind a lot of these dictates where the filters are used, and it kind of like says, well, you would use this filter for this certain application. So analog, as we discussed, like digital, is quite difficult to program. It's very difficult to make a really nice sounding resonant filter in digital, when compared to analog, at least. You can make analog filters very, very small, very, very cheaply when compared to the digital counterparts. So yeah, as we said, simplicity. Stability as well. Digital filters can become unstable and crash and just generally sound really horrible. They're cheap, and you also get the warmth factor, which everyone knows about. You get these kind of almost inaccuracies in analog circuitry that actually sound really pleasant when compared to the digital circuits. They're very, very kind of predictable. So that's a really, really basic analog active filter. It's just two RC networks and then followed by a buffer. So as you can see, we don't actually need much to do this. This circuit would cost maybe £1 if you went and bought expensive components. So voltage control. We're controlling the cutoff frequency with an external voltage. In synthesis, signals are generally described in volts. I gave this kind of talk to a group of audio engineers, and they couldn't understand why we were using voltage control and talking about volts rather than decibels. I mean, volts are obviously kind of more applicable within synthesis. And we need this tonal shaping. We need to be able to kind of make all of these sounds where the harmonic structure of the waveform changes over time. So we want to be able to apply like an envelope and an LFO to the input oscillator of whatever source we have. So you can build these filter stages from just a resistor and a capacitor. And if you chain a lot of these together, the filtering becomes steeper and steeper. So that also means that we need to be able to change that resistance of each RC network. And really, generally, the question is, how can we achieve voltage controllable resistance? Voltage controllable capacitance is generally very, very difficult and just not done. So the first guy to really do this was Bob Moog in his transistor ladder filter. It's probably the most famous filter. Anyone who's into synths here will definitely know it. Probably love the sound of it. It's generally kind of seen as one of the best filters. It's also one of the few patented synth circuits, which means it's really quite important. But Bob Moog was pretty much taking a bipolar junction transistor, which is just a basic transistor, and taking across the base and emitter, there's a kind of internal resistance. And he said, well, if we change the current through this transistor, we can then change the resistance. So this goes back to the RC network. We then have a current controllable resistance. So, as I said, bias current of the BJT controls resistance. And we need an OTA in here to convert a voltage to the current, the bias current that changes.
Finlay?
Yeah.
Can you just tell me, I don't actually know what OTA stands for.
An OTA is an operational transconductance amplifier. So that's a ridiculously long term. It pretty much just, in a basic form, converts a voltage to a current. It's a really, really simple thing. And we also need, because we're using transistors only kind of work one way, as it were. So they can only work with one polarity, and we need to split the positive and negative parts of a bipolar audio signal into the positive and negative. Is everyone kind of following, or am I going far too fast? Is everyone kind of...
We get the positive and negative.
So say if we've got a sine wave, and we've got the positive regions,
okay.
yeah, so we just need to split those up. And the way that this was done in the transistor ladder actually introduces distortion at the very start. So we already have a bit of a kind of crossover distortion, it's called, where if you try and split these components up, you need to kind of drive the voltage a little bit before it really kicks in. So if you have a perfect sine wave, you'll actually turn the kind of parts around zero a little bit flat. So you already start to introduce harmonics. This is kind of a basic circuit. This was taken from Tim Stinchcombe's paper. If anyone's interested in getting into the real technical side of this, definitely go and read his papers because they're beyond me. They're really quite deep. But this is generally how the kind of transistor ladder works. At the bottom, you can see we've got a control current for the cutoff frequency. That's taken from the OTA. And then above that, we then feed the input into Q1 and Q2. They split the waveform into the positive and negative components. And then as you can see, we've got 4 pairs of transistors with a capacitor linking the two. And this effectively forms our 4 RC stages. But if you think of the R, the resistor, as a pair of transistors. So this means we've got a 4-pole filter, which will give us a cutoff slope of 24 decibels per octave. And then at the top, we then kind of bring those filtered positive and negative components back together into a bipolar signal and take it to the output. So there's a few features of Moog's filter which make it really actually sound like the Moog ladder. I think the most noticeable is that when you actually start bringing the resonance up, the audio in the passband of the filter, so that's any audio that is let through the filter, actually is attenuated, so it becomes lower in volume. But the actual resonant peak is getting louder and louder and louder. So that's meant to say full resonance. Full resonance, the signal is actually attenuated by 12 decibels, which is quite a lot. And this is one of the key features. You can hear this when you bring the resonance up on Moog filters when it's fully open. It just becomes quieter. And again, from Tim Stinchcombe's paper, this is kind of what the general function looks like. So you start off at the kind of top curve with a very nice slope. Then as you bring the resonance up, you get this nice peak, which then comes down. But can everyone see you're bringing down the level of that passband? Has everyone got that? Cool. Okay. So Moog's filter was patented, and other synthesizer manufacturers are kind of like, well, this is a really cool idea, but how are we going to work around it? And this is where diode ladder filters came in. So a transistor is pretty much kind of made up of 2 diodes connected in series. And really the first guy to take advantage of this was David Cockrell in the VCS3. So the VCS3's low-pass filter is a diode ladder. It's very similar to the Moog ladder in terms of actual kind of layout, but it uses these diodes rather than transistors. Also, the 303 has a diode ladder filter. And of course, famously, ARP were threatened by Moog with legal action when they tried to copy the transistor ladder. So Moog were actually pursuing this. First of all, the cutoff and resonance controls aren't actually dependent. When you start to bring up the resonance in a diode ladder filter, the filter will kind of squeal more easily at a higher frequency rather than a lower cutoff frequency. And this is actually quite an important feature again. Acid house, this is an absolutely bizarre thing, but when you've got a 303, you're modulating the colour frequency with a decaying envelope. So that means that at the kind of higher portion of the decay, you get more of a squeal out of the filter, and then it comes down and you get just a more kind of like average filtered sound. So that starts to kind of make a whole genre of music. So I kind of saw in my head that you've got this bizarre thing that because Moog patented this filter, maybe you wouldn't have acid house. I don't know. That's a complete theory. But yeah, diodes are completely passive, so none of the runs are buffered. And this introduces a lot of distortion through loading each successive stage of the ladder. So you've already got something that was kind of fairly linear in the Moog filter, now actually becomes very non-linear and very, very kind of distorted and quite nasty. Interestingly enough though, people often actually use transistors as diodes. So you'll often see a diode ladder filter, but they're using transistors configured as diodes, because you can use a transistor as a pair of diodes. So they're just using one diode of each transistor. Is that, everyone good with that? They aren't configured in the same way as Moog was though, so it's not really kind of, you know, a usage of his patented circuit. Also, transistors generally a bit more linear, so we don't get so much of a clipping effect. It doesn't sound as distorted as using just straight diodes. You get more of a kind of saturated feel, and transistorized diode ladders sound a bit warmer than just like straight up normal diode ladders. It's quite interesting. I've built a couple of the VCS3 filters, used one that was just diodes and used one that was transistorized, and they're completely different characteristics entirely. So this is a thing, were people able to kind of, you know, mirror some of the Moog's characteristics? Well, yeah, we've still got the passband attenuation. So, kind of when you use a diode ladder filter, without bringing the resonance up and hearing some of this kind of non-linearity and the distortion, you actually might be fooled into thinking it's a Moog ladder, because we've still got this passband attenuation. So that's quite a nice feature. Korg then also came along in the late 70s with their MS synths and did things completely differently. These filters are absolutely nuts. People have used them, people have heard them, you'll know what I'm talking about. They're absolutely insane. So yeah, they're often sought after for these. And this is down to the Korg 35 chip, which actually isn't really a chip, it's just a pair of transistors encased in some resin. So they take, again, a pair of transistors, but actually kind of flip them. So they're not in the way that they should be used. They're actually completely distorted. So this goes back to our standard analog filter layout. And can you see that they've just taken the resistors and replaced them with these transistors? Is everyone following that? Yeah? Cool. So we've got something called the Sallen key topology, which is just that circuit diagram that I showed you guys. This gives a shallower roll-off, so you don't actually hear so much of a filtering effect. You're letting more of the actually cut-off band through. And you also have a pair of limiting diodes in the feedback loop of the op-amp, which then, again, add even more distortion. So you've got a very, very, very non-linear device here. As you can see below, the green trace is a normal sine wave, and the red trace is just a clean sine wave fed through this filter. So you can see it's kind of been squished, and as soon as you do that squishing, you add harmonics. So you can hear kind of, you know, you haven't got a pure tone anymore, you've also got octaves up with it. We've also got Vactrol filters. So Vactrols are just a pairing of an LED and an LDR, or any light source in an LDR. Could be a light bulb. And this gives, of course, through an LED, current-controlled brightness, and the LDR is kind of brightness-controlled resistance. So you've then got current-controlled resistance. This was really famous in the Buchla low-pass gate, which again, if people have heard it, they know the characteristics of this. It's a very natural-sounding filter for various reasons. The core of the LPG is, again, a Sallen key, so it's actually a similar core topology to the Korg MS filters, but it's got a completely different sound to it, just because of the way that the filter's being controlled. So again, there we take our two resistors, and they're actually being controlled by this light source now. So, if you guys can see that, the Vactrol, you've got this light emitting diode on the top, and then the LDRs on the bottom are being controlled by that LED. Does everyone get that? Is that good, generally? Yeah? Okay. The only thing is this is actually very non-linear in terms of control. So where all of the other filters, you can kind of just about make them track to like a musical standard. So you can connect up a keyboard, set it to oscillate, and then play a tune on it. You can't really do this with Vactrol filters. It's very, very difficult to do. You need some very, very kind of generally difficult to engineer electronics at the front end to be able to do this. So yeah, if you want to do 1 volt per octave stuff with your filter, don't go Vactrol. Also actually matching these components is really difficult. LDRs and LEDs generally in their manufacturing process are very difficult to make the same. You also have a very slow response time, again due to the LDR. So you can't do things like FM with a filter. You can't do very, very fast modulation with Vactrol filters. But this actually also has upsides because, for example, anyone who's used a Vactrol filter, I'm sure, has done this. You can send in trigger signals and do the whole kind of like slewing thing. So it's very good for like percussive, like decaying sounds because you can simply use it very easily. One interesting point though is because the LDR is actually a very linear device in terms of the signal passing through it rather than the control, Vactrol filters are very, very, very good at keeping the signal clean. So if you want to build something like a controllable EQ or something like that that is going to be used with kind of just general audio signals rather than in a synth, you should probably go with a Vactrol filter. The last topology I'm going to talk about is the switch capacitor. This is quite rare. There's only really a few designs that I know of that use it. But here you can take a capacitor and you can charge it, discharge it at a very, very fast rate. Then it actually acts as a frequency controlled resistor, depending on the frequency of the switching. So we typically use analog switches, so you can get these in little chips, or you can use transistorized circuits to do this. Just to switch between loading and then discharging the capacitor. And you can also kind of change that switching pattern to then also change the characteristics of the filter. So here again we have like an active filter, but instead of our resistor we've got a switch loading a capacitor very quickly. So, first of all, as soon as you put this switch in and you start switching at a very, very fast rate in the audible spectrum, that's going to bleed straight through into the filter. So this isn't going to be very good for like pro audio situations where you need EQ or whatever. And you also need a voltage control oscillator now, as well as your core filter circuit, to be able to use this as a VCF. The thing is that we can then actually engineer our VCO to do very interesting things to this switching. And we can also make it very precise. So this is possibly a good option if you want kind of musical tracking to 1 volt per octave and you want to be able to play a tune with your oscillator filter. And you can also kind of add interesting things to your oscillator circuit, so have very kind of, uneven waveforms and be able to switch your filter with these very, very odd kind of square patterns. So I did some tests kind of after writing this, just to really prove a point of kind of the things that I'd found. I ran just some tones through each filter type out of what I could find, and this is plotted on an audio precision system. So this is pretty much giving a graph of the voltage response on the y-axis against the frequency. Everything was tuned to kind of 1K, so you've got a supposed cutoff of 1K. Again, depending on the filter type, you can kind of see it here. Changing the resonance actually, again, changes the cutoff. So you can see that we start to have like resonant peaks here, down at like say 500 Hertz, when they actually should be at 1K. And this is just from changing the resonance, not from the cutoff. So the EMS one, it's kind of an interesting bell curve. There's some degree of like a low cut in there as well. But as you can see from kind of the pale green and purple graphs over here, you get this very, very sharp resonant peak, and especially in the purple when you're at full, you then get second and third harmonic distortion. Second harmonic distortion is quite sought after. Generally, a lot of tube circuits exhibit this behaviour, and third harmonic is pretty common. But I thought that was quite interesting. You get this very like distorted sound out of these early diode ladder filters. Coming up to a more, well, very much more modern filter. This is a diode ladder filter that's been transistorized. So as you can see, we're now free of any distortion, and we've still got this like quite sharp resonant peak. So that kind of again proves the point that, you know, if we use transistors in the place of diodes, we're actually getting a far, far smoother sound. Coming to the MS filters, this is a bit of a mess. Hopefully you can kind of see that between, back a bit, between that and those curves, these are a little bit sharper than these. So because we're actually halving the number of filter stages we've generally got a rounder resonant peak. We've kind of got a shallower cutoff as well as we bring the resonance down. But as you can see at the top, when it starts to self-oscillate, everything just goes a bit insane. And you can't really follow these filters very well at all. Like they're very, very non-linear in terms of audio. So I thought that was quite interesting. You know, you feed the audio through all of these very non-linear circuits, and you can see from the graph that it's crazy. It's absolutely all over the place. Comes to the booklet one, things get far more kind of sensible. We can see that generally we haven't got much distortion, and we've got kind of a nice resonant peak. What is interesting is that we've then got a notch around 4K. So this is from, again, if people have used Vactrol filters, you'll notice that you can never quite close the filter. You always get some audio bleed through. And this is just inherent in using Vactrols. Now what actually happens is that when you start cutting off the audio, you then start shifting the phase. And towards 4K, we've hit about 180 degrees out of phase, so the audio is actually flipped. If you then sum that back into the audio that's bleeding through, you completely remove all of the audio. So you've got absolute, well, close to absolute zero at 4K. So it's interesting that this filter has a kind of like notching effect as well. And you can kind of almost hear that sometimes when you're using it. You get this high shelf of the bleed through as well. So generally, the sound of a synth is typically governed by the VCF style that's used. So mode transistor, diode, OTA, Vactrol, the Korg MS series, they all have their own distinct sound. And that character is typically governed by the actual control circuit we use, not generally the filter core. I found that quite an interesting point, the fact that the sound of the filter isn't actually kind of like based on the audio path that it follows, but more kind of the control path that's used. And each topology has its own kind of non-linearities and distortions, which are all quite different. And as we kind of briefly discussed, you might even have a whole genre based upon this distortion. Analog filters still have their place in audio because they're simple to build, they're easy to control. Digital filters can be unstable. They're very easy to clone like, over and over and over again if you're programming a DSP chip, but it can be quite time consuming to actually code that in the first place. And it's also difficult to model the non-linearity of an analog filter in code. It's generally a very difficult thing to do, and few digital filters have achieved kind of such transparent models of analog filters. They're just simply easier to implement with the original analog electronics. So I'm hoping that if any of you had the burning question of why do analog filters sound different to other analog filters, that kind of answers a few things. I'm sorry if it was really technical. I kind of hope that everyone's followed it to a degree. If you've got any questions, I'll gladly take them. I can't promise that I can answer them. Go ahead.
So a 303 filter,
yeah.
People attribute that to being at 18 decibel approximate. Is that true, or is there something else?
Tim's distinction paper is really good to read on this.
Right.
he says that there are three kind of diode and capacitor runs up the ladder.
Yeah.
So theoretically, it kind of should behave as an 18 decibel per octave filter. For some reason, I presume in the loading of the diodes as you go up the ladder, the non-linearity of it actually behaves more like a 24, I think.
Right.
If you can kind of read through the technicalities of his paper, it does explain it. I can't really remember. I think it's to do with that non-linearity.
Right.
But it is as constructed as an 18 decibel per octave, but behaves as a 24. It's a very interesting thing.
So that's good. Definitely got a unique.
Yes, yeah, for sure.
So what kind of filters are wasp then? Do you know?
I
Because I know it's a weird one.
think it was a switch. Was it switch?
Schmaltz, I think.
Yeah, it was switch cat, wasn't it?
I thought it might be because there was an awful lot. If you send a control signal, there's an awful lot of Bluetooth.
Yeah. Yeah. So I think the ones that I could think of are the Wasp. Ken Stone did one from the Electronote stuff, and there's the Harvest Man one. I think the Barney Lester module. Those were the only few that I could think of. I don't know if anyone's. Yes, yeah, that's true. Yeah, Jürgen did one.
I think he patched some extra distortion in them, if you know what
That'd be typical. But yeah, I think that's it.
Go on then, obvious question, what's your filter? Based on?
My filter's kind of an amalgamation of different things. It's kind of halfway between the Korg MS and one stage of the Moog ladder, but it's not quite either. It's a bit different, but yeah, it's very non-linear. Has anyone else got any?
Yeah, if you look into like the way different filters have different kind of resonance, kind of flavours and such, but that like pre-filter saturation of the VCOs going into it, that can affect a lot of things.
Yeah, that is.
Like the Rolands are very clean, you can't really overdrive, and the Moogs and the Pro 1s you can overdrive, and the resonance stays the same with the Pro 1, but then when I move the whole thing goes up, doesn't it, sort of thing.
That's a very good point. I didn't look into that in this paper at all, but it's interesting how kind of you can change the way that a signal definitely goes into a filter, and also kind of what it does out to the filter core, and it can completely change the characteristic. I mean, look at the MS filters as well. Those diodes in the op-amp path, they don't really seem to have any purpose. They've just been put in because Korg wanted extra distortion, which is really interesting. I kind of thought, at that point in time, you wouldn't have really engineered that in, but they did. Yeah.
Something that I've noticed, some filters seem to behave differently depending on the orientation of the waveform. Not square as the same, but
Okay.
like using a soul wave one way and then the other way. Sometimes what's going on for that?
That's probably, are you hearing that in kind of like the Korg filters and stuff like that? It's probably because of the way that they're using like a very non-linear element at the start. So for example, the Moog ladder, you've always got that cutting of the positive and negative portions. In something like the Korg, you don't at all. You just feed it straight into a transistor that can't actually take bipolar signals. So you're probably altering
How it behaves.
kind of the waveform at the start of the filter, I guess, I presume, but I wouldn't be sure.
Cool.
Anyone else got any questions?
Is there a Moog 2-pole and 4-pole? Do they attenuate the source material in a similar way?
Yes, they do. Pretty much the 12 dB kind of attenuation is from the 4-pole. So I expect that if you go 2-pole, you would get 6 dB. From 1-pole, you'd probably just get 3. So. Anyone else?
Probably
Good.
leave that there.
Yes,
No.
lovely. Thank you for listening, guys.
Yeah, thanks
Once
very
again,
much.